This conference will now be recorded.
Hello everyone. We are starting a new chapter today, which is polymers. So first you have to know what do we understand by polymer. Okay. So this term is derived from the Greek word which is polymeris, and this means having many parts. Now having many parts that you have also seen in the last chapter that we have finished, which is biomolecules. There are also several examples of this type of molecule we have seen, where a single unit is repeating again and again. Okay, so same concept is here also. As a definition of polymer, we can say a polymer is a large molecule, high molecular mass, and it is formed by repeating bonding of many small molecules, and these small molecules will be called as monomer. Okay, remember in nucleic acid what we have seen, the monomer unit is nucleotide, several nucleotides together when it is attached. Now we get the big, very high molecular mass, very large molecule, which is nucleic acid. So same thing is here. So that is one of the example of polymer. So now this chapter is all about polymer. That is its classification based on different uh, things. Okay, so it may be we'll come to that point. So classification and then how we can synthesize and also their application. Fine. So polymer is the repeating unit, that is the small unit, and large number of monomers together when connected, then it forms polymer. And the process by which it happens, that is known as polymerization. That is the name of the method. So here we have some examples. PVC, the full form is polyvinyl chloride, PVC. So as we are saying polyvinyl chloride, that means vinyl chloride is coming several times. That is why it is polyvinyl chloride. Just focus on this term. So this should be the monomer. So here the name of the polymer is polyvinyl chloride, or in short PVC, and the monomer unit is vinyl chloride, which is basically the repeating unit. Here we can see some examples in the right hand side, and the first examples that you are seeing, these examples are basically natural polymer. Okay, that you can already see it is obtained in nature, in biology, in animals or in human body, whatever it is. And the other box that you are seeing below it, here we have some example: nylon, polyester, teflon, epoxy. So this can be man-made. Fine. So as polymers are very big sized molecule, and here from the value 10 to the power 3 to 10 to the power 7 unit, it actually the unit which is used for very large molecule, it is also known as Dalton. Okay, so this small u, it is used for large molecules to express their molecular weight. From this value we can understand their size is very big. So that is the reason they are also known as macromolecule, because the term macro means very big, something very big. Polymers classification is possible based on different things. Okay, so the first we will see how we can do the classification based on source or origin, that is from which you are getting the polymer, whether it is natural or synthetic, something like this. So it means based on source or origin we can have different types of polymers. The second is structure. So what type of structure is actually present in the polymer? Different types of, that is when the monomers will be attached to each other, there will be some new linkage form. Just you have seen when two amino acids are joined together, ultimately we get a polypeptide molecule. So the linkage part is basically peptide bond. So same thing is also here. Depending on what type of linkage is present, we can have some classification. That is the second classification. The third classification is mode of polymerization. Okay, so how the polymerization is actually taking place, when it is happening, that is when you are making the polymers, that depend based on that method we can have classification. And the last one is molecular forces. What type of molecular forces are present in the polymer, based on that also we can have classification. So next we will see all this classification in detail with proper example, picture obviously, one by one. Okay, so classification, as you can see the whole picture, that is the flow chart. Types of polymers classification is possible based on origin, that is number 1. It may be based on structures of polymers, which is number 2. It may be based on mode of polymerization, that is number 3. And molecular forces. So all these 4 points you have already seen in the previous slide. So when it is based on origin, it may be natural polymers which are already present in nature. You don't have to synthesize. It may be synthetic, which is completely man-made, and something may be in between these two, semi-synthetic. So that means it is not completely synthetic. Suppose you have some natural polymer, you are making some changes in the structure, then it will be under this category, semi-synthetic, not completely natural, not completely synthetic. Then we have based on structure, linear polymer, then branch chain polymer. So branch chain means there will be some branching present, substituent, and cross-linked or network. So cross-link, that means each chain that will be connected to each other. Fine. Based on mode of polymerization. So when you are actually making the polymer, how you are making the polymer, depending on that also you can have classification. So here we have 2 types, addition polymers. So when you have taken several monomers, you are just simply adding them. You are getting, so this method is addition polymerization. But suppose you have taken several monomers and there is some condensation process going on. Now condensation means removal of some small molecule. Okay, so we'll see when we'll actually discuss this in detail. And the last, based on molecular forces. So in the final polymer that we have, what type of molecular interaction or forces are present, based on that also we can have some classification. Elastomer, fiber, thermoplastic, thermostatic. Okay, so first we'll start with based on origin or source. Based on origin. So from where it is actually we are getting. One of the common classification of polymers is based on source, that means from which the polymer is derived. Natural polymer. These polymers, as the name suggests, they are obtained. Sorry, there will be a gap. The polymers that are obtained from nature, that is plants and animals, we will call them natural polymers. So some pictures you have already seen. Protein, nucleic acids, cellulose starch, all these we have already discussed, right, in the last chapter, which is biomolecules. Another example is natural rubber, that is also obtained from plant. After natural polymer, synthetic, that means man-made. So they will be synthesized in the laboratory. Here as example we have polythene, synthetic rubber. The previous one is natural rubber. Now we are calling it synthetic rubber. Then we have, it is also known as guanase. Then we have PVC, polyvinyl chloride, monomer is vinyl chloride, and nylon 6,6. So all these are examples of synthetic polymers that are man-made, we can make in the laboratory. Semi-synthetic, that means not completely natural, not completely synthetic. Polymers obtained by making some modification in the natural polymer by artificial means. So you will take some polymer which is natural in the laboratory, you will make some changes in the structure. So for example, cellulose is a natural polymer, right? Now if we do acetylation with acetic anhydride, acetic anhydride is this structure CH3CO OCOCH3. So this is called acetic anhydride. So this molecule is used for acetylation process. If there is any OH group present in molecule, if you are using this compound, which is in short we write it like this, Ac2O, then what will happen? This OH will be converted to OCOCH3. So this COCH3 that we are getting from Ac2O. So this process is acetylation. So if OH group is present, cellulose there is OH group present. In presence of this acetylation reagent, which is acetic anhydride, we can get OCOCH3. So this is as if we are doing some modification in the natural polymer. So that is it is semi-synthetic. Okay. So on acetylation with acetic anhydride in presence of sulfuric acid, cellulose forms cellulose diacetate polymer. Some other examples: cellulose nitrate. So here nitrate group will be inserted. Then vulcanized rubber, which is a modification of the natural rubber. Fine. The second classification, which is based on structure. What type of structure? Branching present or not, network present or not, or is it very simple? The first one is linear polymer. So obviously it will be very simple. Linear, simple chains will be there, no branching, no network. These are the polymers in which monomer units are linked to one another to form long linear chains. So several monomer units, they will be connected to each other and you will get a long chain. So here you can see total 4 chains are there as if they are parallel to each other, but they are not connected. These linear chains are closely packed in space. So as there is no branching, they can come close to each other. Closely packed structure is possible. As a result, as they can come close to each other, they are closely packed, there is less space available. So that is the result. Now the density will be very high. And when density is very high, that is mass per unit volume, that value is very high, tensile strength, okay, so that will also be very high. That is the resistance to breaking, that is the tensile strength, that will be high. And obviously melting point is also high. Examples under this category is high density polythene. So there are, polythene is a term that we have seen as example, but remember this may be two types: high density, low density. So when it is linear structure, it is high density polythene, because we have already seen in linear structure close packing possible, so density will be high. So that is why example is high density polythene. Remember, in this way, suppose you are trying to memorize some examples. So if, as the name, from the name you can understand high density polythene, so it will be obviously under linear. Then polyvinyl chloride, PVC, nylon, polyester, etc. Structures we will see obviously. Branch chain. So the pictures that you are seeing here, that is the simplest way by which we can understand all these types of polymers. Branch chain. So after linear, if you have some branching in the polymer, so in such polymers, monomers are combined to form long chains, and there will be some side chain or branches also, and they may be having different length. Because of this branching, now they cannot come close to each other. Each chain, they cannot come close to each other. So as a result, what will happen? They will have low density. That is important difference with linear polymer. Tensile strength is also low, resistance to breaking, as well as low melting point. So if you compare these 2 points, they are actually completely reversed, right? Example, low density polythene, starch, glycogen. So as you can see from this structure, you can understand from the simple structure, several branching is there. Okay. Cross-linked, it can also be called network. In this type of polymer, the monomer units are linked together and it will form some three-dimensional network. Don't be confused with the other one, that is branch chain. These two are not same. In branch chain, what we are seeing, in each chain there is some branching. But now what is happening? You have some, as if these are the linear polymer, but one polymer, it is connected to other by some linkage. So that is why it is cross-linked. Okay. Now because of this cross-link, some three-dimensional network generation is possible. Expected to be quite hard, rigid, and brittle. Under this, we have example bakelite, glyptal, melamine formaldehyde. So the example name that you are seeing here, when we will actually discuss their synthesis after finishing classification obviously, then you will be getting proper idea what is the structure. Okay, because if you don't look at the structures, you will not be able to understand what is the monomer, how they are connected to each other, and finally you are getting polymer. Because the question that you will get from this chapter, it is mostly you can get that sometimes some structures will be given, and from the structure you have to understand what type of polymer it is. Okay. Now the third classification, based on the mode of polymerization, that is how you are actually making this polymer. Based on that also classification is possible. So suppose we are doing this by addition polymerization. So that is why these polymers are known as addition polymers. These polymers are formed by polymerization of monomers containing double or triple bonds. That means they will be unsaturated compound and they will be connected to each other by simple addition. There is no removal of small molecule. Addition polymers have the same empirical formula as their monomers. Okay, so that is important information. And we can have two classification under addition. So under addition, it may be homopolymer and it may be copolymer. So as the name suggests, when it is homopolymer, all the monomer units are same. You can understand from this picture. But when it is copolymer, there may be more than one monomer and then they are repeating. So this is monomer number 1, this is monomer number 2. So these two are repeating again 1, 2, 1, 2. But here it is only 1, 1, 1 like this. Not necessarily it is 1, 2, it may be 1, 2, 3, 1, 2, 3 like that. Okay, but minimum at least 2 different monomer must be required for to understand copolymer. So it is homopolymer which are obtained by the polymerization of, sorry, it is single, it will be single. It is actually, when I have typed it, it is just exchange. Single type of monomer, that will be in this case, and 2 or more monomers, that will be for this. Okay, so they are known as homopolymer. So for example, here also just by mistake it is exchanged. Fine. So for example, polythene monomer unit is ethylene, and PVC, where the monomer unit is vinyl chloride. So polythene, as the name suggests, polyethene, that means ethene molecule is the monomer unit which is coming, that is repeating several times. So only one monomer unit, but copolymer there will be at least one extra. Another example of homopolymer PVC, where vinyl chloride is the single monomer. When it is copolymer, examples are Buna S. Okay, this is a copolymer of two monomers. The first monomer is 1,3-butadiene, which is containing CC double bond. Another one is styrene. Now this is also containing CC double bond, but that is attached to benzene ring. Obviously, we'll see the structure. So as we are doing only classification, so I have not added the pictures. When we discuss the synthetic synthesis methods, you will get proper idea about the structures. So this is addition polymers, and the second one category under mode of polymerization. How the polymerization is actually occurring. The second one is condensation. So condensation polymers, they are formed by combination of monomers with the elimination of small molecule. So now there will be removal of some small molecule. What type of small molecule? Mostly it is water. It may be alcohol also, or it may be removal of HCl also. So as there is some small portion is removed, so that is why the name is condensation. Remember, in organic chemistry, we use the term condensation reaction. That means just in case of aldol reaction, we use the term aldol condensation. Why? Because water molecule removed, we get some CC double bond. So that is why it is aldol condensation. But if you only consider the first step, it is aldol addition. But in the second step, when we are heating the aldol product, addition product, and then water molecule is removed, you should now call it aldol condensation. So the first step is addition, but in the second step, as water molecule is removed, it is called condensation. So the same concept. Some small molecules were removed, we call this condensation. So because of this method by which it is formed, we are calling these polymers condensation polymers. Example, terylene or dacron. Both the names are actually for the same structure, but two names. Sometimes terylene you can get in question, sometimes dacron will be mentioned. So that is why you should know both the terms. Nylon 6 bakelite. One example you will see here. Dacron. How we can make dacron or terylene. So here we have taken two different uh, monomer, though you can say that it is a type of copolymer. But remember, when copolymer, yes, that is also true because we have taken two monomer, but the copolymer that we have discussed under addition polymer, you have to keep the addition part fixed. So if you have taken two different monomer and you are doing the process by addition method, not condensation, then you can call it is addition as well as copolymer. But in this case, it should be called condensation copolymer. Okay, and mostly we'll see in condensation you hardly get any homo polymer. I mean these previous homopolymers where same monomer unit is used. That is mostly we do not get. So most of the cases in condensation it is to different monomer. So that is why individually we do not do the classification that it is homo and copolymer. Fine. So the first monomer n number of monomers we have taken, and the name is terephthalic acid. Phthalic acid is basically benzene ring containing two CO2H group, and depending on the position of these two CO2H, 1, 2, 1, 3 or 1, 4, different types of names may be there. So in this case, we are calling it terephthalic acid. Teri because of its position 1, 4. We have taken n number of this molecule, and ethylene glycol n number of this molecule. So in ethylene glycol you have OH group alcohol, and in terephthalic you have acidic CO2H. So we know the reaction between acid and alcohol, we get ester. So same type of reaction we take. So just remember the simplest example of esterification. Suppose we have ROH and RCOOH. This is R. So if this is the esterification we are doing, so what happens? Here this OH and H is removed. As a result, we get RCOOR prime. So here this water molecule is removed. Net removal of water is taking place. Here also the same thing. What will happen? This OH and H will be removed. As a result, you are getting this type of ester linkage. And this will happen both sides of terephthalic acid. And if you consider from the point of view of ethylene glycol, then also both sides there will be loss of water. So this is the repeating unit which is mostly written in this fashion within third bracket, and we have mentioned n. That means it is repeating n number times, and we have started with n number of terephthalic acid monomer number 1 and n number of ethylene glycol monomer number 2. Fine, but here important thing is removal of water molecule. So that is why we are discussing it under condensation polymer. Now the last classification, which is based on what type of molecular forces present. Under this classification, the first possibility is elastomer. So from the picture you can get some idea, and as the name suggests, elastomer, that means we can easily stretch it. So those polymers in which intermolecular forces of attraction between the polymer chains weakest, and there is some elastic type of character. So that is why we are calling it elastomer. Now as it is very weak, these polymers can easily be strained by applying small traces, and when this trace is removed, it can regain their dominant shape, original shape, when the stress is relieved. These polymers consist of randomly coiled molecular chain. So as you can see, randomly coiled molecular chain, but when you are stretching it, these coils are to some extent, now they are less in number, right? So that is why stretching is possible. Then again, if you remove the stress, it is recoiling it. That means again coils like this Coil means this type of coil structure will be there. Okay. So this is the before and after stage. The left hand side before stage, right hand side after stage. Examples: natural rubber, Buna S, Buna N, and neoprene. Here we have some pictures. Natural rubber, and here you can see the repeating unit. This part is the repeating unit. Then neoprene. So the repeating unit, it is already written within bracket N. So 4 carbon, CC double bond, and in this carbon there is chlorine. So this is called neoprene. Example of elastomer. Then Buna N, and repeating unit within third bracket is shown, and Buna S. Okay. So these are the structures of these 4 examples that are mentioned here. The second one, under the classification based on molecular forces. Fiber, number 2. Fibers belong to a class of polymers which are thread-like, and they can be woven into fabrics. Because of this thread nature, we can make fabric. So that is why the name is fiber. Widely used for making clothes, nets, ropes, gauze, etc. Tensile strength is very high, and because the chain possesses strong intermolecular interaction. So in the previous case, we have seen intermolecular forces are very weak. Now it is strong. What type of intermolecular interaction? Dipole-dipole interaction. Then hydrogen bonding. So all these are really very strong. Different types of intermolecular forces are there. Among these 2 are strong. Okay, and it is also having some crystalline nature and sharp melting point. Nylon 666,6. Then terylene, also known as dacron, and polyacrylonitrile. So sometimes you can find same example you have also seen in other category. But remember, when you are doing classification based on any particular type, that is molecular force or origin, then the examples that are given, that is based on that particular thing only. So here we are discussing it molecular force. Okay. So obviously, as this type of strong molecular forces are present, suppose it is present in terylene. So that is why we are discussing it under, we are giving this example of terylene. But that doesn't mean that you cannot get this example in any other classification type. Because suppose there is another classification which is based on what is the method by which you are making it. So in that case also maybe you are giving the same example. So that is also possible. So that is why same example you can find in different polymers, polymer names. So here we have the structure of nylon 6,6. Here we have amide linkage. So all these are amide linkage, right? And each chain, if you consider, this is the first chain, second chain, third chain. The chains are connected to each other by hydrogen bond. How the hydrogen bond is occurring? The H of NH group and the oxygen of C double bond O. So because of this hydrogen bonding, which is strong, we are getting this type of fiber-like structure. So here the carbonyl oxygen and amide hydrogens can hydrogen bond with each other, and that is why it can form, it can line up in orderly fashion and ultimately form fibers. So this is example of nylon 6,6. Then polyacrylonitrile, CH2CN, CHCN, which is the repeating unit, and terylene on dacron, that you have already seen this example under condensation polymerization. Remember, because when you make it, you are removing water molecule. So that is why we have given the same example under condensation polymerization. And now we are giving it because it is also having strong intermolecular forces like hydrogen bonding or dipole-dipole interaction. After fiber, there are 2 more types, thermosetting and thermoplastic. So first see what is thermoplastic. These are linear polymers and have weak van der Waals forces acting in different chains. So now the force is again not very strong. These most forces are intermediate of the forces that is present in elastomer and fiber. So very clear. Now you can understand. So for elastomer, it is the weakest. When we are saying weak, suppose I am saying polymer number 1 is weak force, polymer 2 that is also having weak force. So how you will compare? So it is true in both cases, it's true. In both cases it is weak. But in elastomer it is the weakest interaction. And fiber it is very strong. And something in between that is present in case of thermoplastic. When we are heating it, they can melt and it will be a fluid type of nature. Now again when it is cooled, it will set into a hard mass on cooling. So because of this particular property, we can make different types of shape simply by heating it and then cooling it. And obviously you have to use some molds for that. Example, polyethylene, polyvinyl chloride, PVC, polystyrene, styrene is the repeating unit, polyethylene terephthalate, which is another example. In short, PET, polyethylene terephthalate. Okay. Here we have example polystyrene. So in polystyrene, the repeating unit is styrene. Styrene is basically PH, then CC double. Polyvinyl chloride. Vinyl chloride is CC double bond, and then we have CM. This is known as vinyl chloride. So this is the repeating unit. Unsaturation is present, and polyethylene terephthalate. So you can find some similarity with dacron, because in dacron monomers are terephthalic acid and ethylene glycol. But in this case, it is again terephthalic acid, but not ethylene glycol. It is different. Okay, it is coming from ethylene. Fine. So these are the examples for thermoplastic polymers. Thermosetting. These are normally semi-fluid substance with low molecular masses. But if you are heating it, now it is becoming hard. In the previous case, you have seen it is becoming fluid. But now it is different. It is becoming hard and infusible. Now why it is becoming hard? Because when you are heating it, some cross-linking is generated between the chains. And because of this cross-linking, now they are becoming hard. So suppose we have individual chains. They are not attached to each other. So they are semi-fluid. Now you are heating it. Then there is some connection linkage is formed. As a result, what will happen? They will be hard. As a result, they can also become three-dimensional because of this cross-linking. Examples: bakelite, melamine formaldehyde resin, urea formaldehyde resin. So here you can compare these two, that is thermosetting in the right hand side and thermoplastic in the left hand side. So in the left hand side, all these are white dots. These are indicating that there is no cross-linking and weak intermolecular forces are present. But here, this black colored, it simply means now the chains are connected. Here also, as if this chain, this is another chain, but as if it is above one chain, it is not connected. It is just above or below. But here, whatever you are seeing, it is actually connected by these black dots. So strong covalent bonds are. So these two, from these two pictures, you can compare thermoplastic, thermosetting. So this is the structure of bakelite. Okay. So see, this is as if one chain. This is another chain. Now they are connected to each other. These are the cross-linked portion. So because of this cross-link, now they are very strong. Okay. So before heating, suppose there is individual chain, it is semi-fluid. Now when heating it, this CH2, through this CH2, it is now connected each chain, and as a result, what is happening? It is having some three-dimensional cross-linked structure. Then we have urea formaldehyde resin, as it is mentioned here. So this is urea molecule NH2CO NH2 and formaldehyde HCHO, simplest aldehyde that is possible. So this NH2, this side, and as if CH2, that is actually coming from formaldehyde. Okay, so this is as if one chain, this is another chain, but see here through CH2 this is connected. Okay, so that is why again we are getting some cross link. So all the classification that is based on origin, then how we are making it, what type of forces are present, based on all these things we have seen, based on structure also. All these four classification and the corresponding examples are discussed. Here we have some polymers given, their structures are given in the left hand side, which is list number 1. And what is their nature? Nature means we have all the names that we have discussed. Remember, actually the 4 names that you are seeing here, 1, 2, 3, 4 in the right hand side column, all these 4 are under the last classification. The last classification is based on intermolecular forces, right? And depending on what type of intermolecular forces are present, we can have 4 types, and these 4 types are actually mentioned here: elastomer, fiber, thermoplastic, thermosetting. But name of the polymers are not given. So that is why, as I have said, structure, if you do not remember, you will be having problem to solve this type of question. Fine. Now fibers, what we have seen, some remember, there is nylon 6,6. What structure we have seen? There is some connection between each chain. Now in nylon 6,6, if you can remember the structure, there is some amide linkage, right? So this example we have already seen under fiber. So you can find similarity with this. This is amide, and then there is CH2, and again this amide is repeating. Okay, so B must be 2. Now see, B matching with 2, this you can find only in option B. So if you are sure about it, then this is just enough to answer, to choose the correct option. So sometimes if you are lucky enough, then you can get this. So it will save your time also. Okay, but suppose if you are sure that A is matching with 3, then this is coming twice. So A is matching with 3 means it is elastomer. Okay, so in that case, now you will be stuck between B and C. But right now, what we are saying, B is matching with 2, which you can find only in option. So that is why there may be a chance that B option is correct. Okay. So this is actually neoprene, which is A, right? This is B. Then PVC, that is polyvinyl chloride, CH2 CHCl. That is the repeating unit. This is C. And the last one, that is this type of structure, that is actually in bakelite. Though the cross-linking part is not shown. Just see in the previous slide. You can find some similarity with this, though 2 chains are not. So this must be thermosetting. So D should match with 1. Okay. So D is 1. Now D1, that is found in both option A and B, but as we know, B is matching with 2. So that is why option B should be the correct. So A is 3, which is neoprene. You can also find the example where we have discussed elastomer, and neoprene is given as example. And B is B already we have seen. Then C is, which is polyvinyl chloride. It is matching with 4. That means it is thermoplastic polymer. Okay. So considering all these facts, this should be the correct option. So in this question, though names are given, structures are there, but it may be that sometime names will be given and you have to find what is the name of the corresponding, that is nature, depend based on the molecular forces. So here the 4 names that are given, all are basically based on molecular forces, but it may not be always so. So after classification of polymers based on these 4 things, next topic will be methods of polymerization. Though we have already seen the third classification, which is the mode of polymerization. There you have already seen the mode of polymerization classification. 2 modes are there: addition, condensation. Remember? So here also actually now we will elaborate that part. So under addition we have seen some examples, some name as example. So all this we will now see how we can actually prepare them by addition. Here addition you can also call it chain growth. That is another name for it. And some polymers that will be synthesized by condensation method, you can also call them step growth polymerization. Okay, so 2 names: condensation or step growth, addition or chain growth. So when it is addition or chain growth polymerization, so we have some primary idea, but now we are going into details and we will see all some examples, important examples of polymers and how they are actually synthesized starting from monomer. So for this type of polymerization, monomers that are used, they are unsaturated compounds. For example, it may be alkene, that is CC double bond. It may be alkadiene, that means 2 double bonds may be present. Suppose 1,3-butadiene. So this is alkadiene and their derivative. Derivative means there may be some groups present. Suppose here we have some group Cl, or here we have some group Cn, like this. So it may be monomers may be alkene, diene, and their derivatives. Chain growth mechanism involves addition of the reactive end of the growing chain. So you will start from monomer, but gradually the chain length will increase. And in the chain, one side will be reactive. Not all the sides are reactive, only one side is reactive, and that reactive side there will be increase in the length. So drawing the chain across the double bond of the monomer. So that if you consider simple alkene, there is some alkene part and CC double bond. So mainly in the CC double bond part, the chain will grow. That is the reactive end. It involves formation of some reactive intermediate, and depending on what type of reactive intermediate you have, is it free radical containing odd electron? It may be carbocation, that means electron deficient, positive charge is present over carbon, or it may be anion, negative charge present over carbon. So depending on these 3 types of reactive intermediate, we can have 3 possibilities under addition or chain growth. So it may be free radical polymerization, then cationic polymerization, and anionic polymerization. And among these 3, this is most important. And examples under this category is also high compared to the other 2. But we have to see all these 3 types under addition or chain growth polymerization. Free radical polymerization. When alkenes are heated with free radical initiator. So suppose you have taken any alkene. In general, I am writing R2C double bond R2. So in this case, you have to generate first the free radical. And to generate the free radical, which is the first step that you have to do, you need some initiator. So some external reagent you have to use. So free radical initiator, very common examples are peroxide molecule. It not necessarily it has to be benzyl peroxide. Or just one example is given, benzyl peroxide, but actually it should be peroxide. Peroxide in general, you can write the structure O, single bond O, and both sides there will be some groups present. So this is a peroxide linkage. So what happens in peroxide? This CC double bond, single bond is broken, and there is odd electron present over each oxygen. It is not positive or negative charge. In this bond, there are 2 electrons, right? So one electron will be present over one oxygen, another electron will be present over other oxygen. So in this way, we can generate the radical. So this is radical initiator. Now this oxygen with odd electron O dot, that will attack this CC double bond. So in this way, the reaction will continue. Now the example we can say styrene. Styrene is PH, CH double bond CH2. PH then CC double bond. If you do polymerization, you will get the polymer which is polystyrene. So when this polystyrene is heated, so you can increase temperature for this free radical polymerization, or you can expose it to light. Okay, but peroxide initiator that must be present. So the different steps that we are going to see, as it is free radical mechanism, and just in any free radical mechanism, not necessary for polymerization. Free radical mechanism you will also find in some other organic reactions. So it is very common in free radical. There are 3 steps that are very common: chain initiation, then propagation, and then termination. So initiation, obviously the first radical will be generated, and the radical initiator that will attack the CC double bond. So in the radical initiator, when it is heated or exposed to light, heat should be very high here, because we are breaking this bond in odd electron over each oxygen. Okay, so first the peroxide undergoes homolytic fission. Homolytic means the fission after which there is single electron present over each atom. It is not that it is O plus O minus. So it is homolytic fission, not heterolytic. For example, benzoyl peroxide. Benzoyl is PHCO, then O single bond O, then again COPH. When it is benzyl, it is PHCH2 OOCH2PH. But now it is PHCO. Benzoyl means PHCO group. PHCO group is benzoyl. And when I am saying benzyl, that is actually PHCH2 group. So this is the difference. But whatever is the group, O single bond O, that linkage must be present. So peroxide undergoes homolytic fission. For example, benzoyl peroxide, on heating, it produces phenyl initiator free radical. So see, this is the picture of benzoyl peroxide, PHCOOOCOPH. Now, when you are heating it or exposed to light, in that case, you have to use this type of sign. There is homolytic fission. See, here single-headed arrow is used. It is not double-headed arrow. Double-headed arrow you can use in electrolytic fission, where positive and negative charge is generated, but not in homolytic fission. As it is single electron over each atom, you have to use single-headed arrow. So there is first generation of PHCOO dot 2 parts will be there, and then this single electron, suppose it is making cis double bond O, so there will be a newly generated bond between carbon and oxygen. So as a result, now this bond will be broken. So finally what you are getting, phenyl radical PH dot, or you can write it in this way, benzene ring single electron, and 2 carbon dioxide molecules will be removed. Okay, so finally we are getting in this step pH dot. Now this pH dot, which is phenyl initiator free radical, it will attack styrene molecule, which is CC double bond then pH. So this carbon, that is the part through which this pH will be attached. Now if you are thinking why it is not attacking the other carbon, so it will not attack the other carbon, it will only attack this left hand side carbon. Suppose this is 1, this is 2. So phenyl radical, it will attack the left hand side carbon, because if it attacks the carbon number 1, then the single odd electron C dot that will be generated just next to pH. So there is some resonance possible. Just you do resonance of positive charge in benzyl position with the double bonds of benzene ring, or negative charge. In a similar way, the single odd electron that can also take part in resonance. So this is stable. So stabilized radical. But if you are doing the opposite one, that suppose you are attacking this pH dot towards carbon number 2, now it will be sterically problematic, as well as it is not stabilized radical. So that is why it is attacking carbon number 1, and you are getting this type of radical. I can also write it like this: PHCH2, then another pH here, and this is the odd electron. Okay, so this is the first step. This chain growth will continue with the successive addition of several thousand of monomer units. So here you are just seeing one step. So then next, this odd electron, it can attack another monomer unit, styrene. So this is step number 1. Step number 2 is chain propagation. So this new free radical, this generation you have already seen, now it can attack another styrene, which is monomer, and as a result, this is again a odd electron which is next to pH, because that is stable one. So that is why it will always attack this carbon which is far from pH, and in this way it will continue and continue. Ultimately, if you look at the structure properly, this part is the repeating unit. Okay, so that is, it is written within bracket, and you can also use third bracket, and then N, polymer chain, CHAIN. And finally, as it is common for any free radical mechanism, this dot, it has to be quenched. It cannot remain in this way. Finally, it has to be neutral. Okay. So chain termination. Now we will terminate the chain. So there is actually several methods by which you can do so. Combination, disproportional, chain transfer. But details you don't need to know. Just remember, in this case, mostly combination mode, which is very common, is occurred. Okay. So combination mode is very simple. You take two chains, as if two polymer chains you have taken. Just this dot, it will be connected with another dot. So suppose you have two dots. Now these two dots are connected. So this is a newly generated dot. So in this way, termination will occur, and ultimately the reaction will be complete. Fine. Now, after free radical polymerization, the next one is cationic polymerization. So as the name suggests, now free radical will not be generated, cation will be generated. Fine. It involves the formation of carbocation. How we will generate it? It can be generated, you can use any Lewis acid. Fine. And mostly BF3, AlCl3, SnCl4. You can also use some protonic acid, H2SO4, HF, like. So here we have taken HA as if it is any protonic acid, and we have taken a general alkene, RCH double bond CH2. So now this double bond, it will be attracted towards the H plus, or if you have taken any Lewis acid, which is electron deficient species, so it will be having some attraction for electron dense region. So that is why this CC double bond pi electron cloud, it will be attacking towards H plus or any Lewis acid, and there will be this type of interaction. See, after taking this H, now there is positive charge generation. As the connection is occurring through this carbon, left hand side, there will be some positive charge generated in this carbon, and this positive charge, A minus is already present in the medium, so there will be some positive negative opposite charge attraction. So this is the initiation. Then propagation. Just you have already you know these terms. In propagation, another monomer unit is there. The double bonds between carbon, the pi electron is again attracted towards this carbon. Okay. So as a result, now what will happen? This part, see, now it is connected towards the other. Okay. Actually, CH3 then CHR. It is here, left hand side part, and then CH2 then CHR. Okay, so now this carbon, there will be this newly generated positive charge, and again in a similar way, just you have seen in the previous case, there will be some positive negative opposite charge attraction. Finally, there should be some termination. So what will happen in the termination step? This H, suppose I am writing one hydrogen like this, so it will make this H will be removed. As a result, you are getting CC double bond. So this H, now it will neutralize this A minus, because this H is removed without electron pair. So it is H plus. So it is now H plus A. And finally, you are getting the polymer. Okay, so this is cationic polymerization. Similarly, anionic polymerization, it will involve carbon, and for generation of carbon, you have to remove some proton, so you need some strong base. Here, what strong base we have taken? N-butyl lithium. You can also write it like this, N-BULI, or you can write C4H9. If I write like this, 4 carbon chain, and then there is lithium. 1, 2, 3, 4. This is N-butyl lithium, which is very strong base. This is actually organometallic reagent. This part is alkyl part. So in general, if I write it like this, there will be negative charge here, positive charge over this. So this is carbon metal bond. So that is why it is organometallic reagent. So this negative charge, which is very strong, it will attack this carbon. As a result, negative charge will be generated in the second carbon. Now, if you are thinking why it is not attacking this one, because that will not happen. If it attacks this left hand side carbon, then only negative charge will be generated in the carbon where CN is attached. Now CN is electron withdrawing group, so it will stabilize this negative charge. So that is why it is occurring in this way. Then propagation, another monomer you have taken, and this newly generated negative charge, now it is attacking again the CH2, and negative charge is generated, but CN group is present, and this negative charge is balanced by Li plus. Finally, we need termination, and for that, what we are using? Suppose we are using some RH. This RH, as if it is providing this H. So it may be any alkene. This H is actually this negative charge. It is very strong, so it can take this proton. This R will be removed, and RLi is the ultimately removed. So we are getting finally the polymer. So we have discussed all the 3 possibilities under addition polymerization. Next we will start condensation polymerization. Okay, so we are at the end of the session. Thank you for listening.